In this video, we discuss the trapezoidal rule. This is the first of two methods that we'll discuss with regard to numerical integration. With the trapezoidal rule, we just take the interval from A to B, and we subdivide it into n equal pieces, or n subintervals, of equal width. So the width is the length of the interval, which is b minus a, divided by n, where n is the number of rectangles. So we always call it x naught a, or we always call it a x naught, and then we have another x value and another x value, and all of those x values increase, or the subscripts increase until we get to x sub n. That's our b value. So the function might look like this. And then the area of the ith trapezoid is just 1/2 of the sum of base 1 plus base 2. So it's going to be the two heights of our function times the height of the trapezoid, if we're thinking of that delta x as the height of the trapezoid. So we end up with 1/2 of the function value at the last endpoint plus the function value at the next endpoint. So that's giving us the average y value on this interval, and then we're multiplying by delta x. Now it turns out that that area actually approximates or gives us the exact area under the curve as the number of rectangles goes to infinity. And we can see that if we say that the area is approximately this, it's a function of n, so it's this. Now, if we expand this by substituting in values for our index I, this is what we get. When I equals 1, we get f of x naught plus f of x1. In these brackets, times 1/2 times the delta x. When I equals 2, we get f evaluated at x sub 2 minus 1, which is 1, plus f evaluated at x sub 2, so that's that. And in the last subinterval at I equals n minus 1, we've got this. So I think it's clear to see just from this expansion or just from this picture itself, we're going to count this function value f at x naught once, and then we're using this function value f of x1 for the first trapezoid and the second trapezoid. And we're using this x value or the y value at this x value here for the second trapezoid and the third. So all of those numbers in the middle, all of those y values in the middle are doubled, but we only use the ones on the end once. So we end up with 1/2 times f at x naught, or f at a, plus 2 times the function at the next x value, plus 2 times the function at the x value after that, and so on. And then finally, we've got f at b times delta x. Now, if we want to, we can separate this a little bit so that we end up with something that looks like a Riemann sum. If we distribute that 1/2, we have 1/2 times f of x naught, or that's also f of a, if we prefer, times that delta x. And then if we distribute this 1/2 to all of these guys, we have f of x sub 1 plus f of x sub 2 all the way through f of x sub n minus 1. So we've got that, and that's being multiplied by delta x. And then we have this 1/2 f of x sub n. So that would go out here. Now, in order to make this look like a Riemann sum, where I have the sum as I goes from 1 to n of the function values, so I'm using my right endpoints as sort of test values like we do when we use the right endpoints as our selected x values in the Riemann sum. The only term that's missing is f of x sub n. So I substitute or I add an f of x sub n here, and that's fine, it's legal, as long as I also subtract f of x sub n times delta x over here. Because when I add that in the brackets, what I'm really adding to the quantity is this times delta x. And so what I'm doing is adding a well-chosen 0. If I'm adding that here, I need to subtract that out there so that I don't actually change the value of anything. Now this value right here looks a lot like the Riemann sum. We're just using the right endpoints of each interval. So you've got the heights of those rectangles whenever we use those right endpoints to create rectangles times the width of the ith rectangle, where our widths are all the same, that b minus a divided by n. And then this 1/2 of this quantity minus one of those quantities gives us negative 1/2 of those. And then I've got a positive 1/2 of f at a times delta x over here. So we end up with 1/2 times f at a minus f at b from this term times delta x, plus that expression that looks like a Riemann sum. And then we can replace delta x with b minus a divided by n and write that 1/2 as a 2 in the denominator. And so we get this expression. This is our area. So if we take the limit now as n goes to infinity, this term goes to 0. And we end up with the limit as n goes to infinity of a Riemann sum, where we're using the right endpoints for our intervals. So that actually equals the integral from a to b of f of x dx. So that's really nice. We know that if we take more trapezoids, we're going to get an even better approximation. So we have a theorem. It says, assume f is continuous on the interval from a to b, then this integral of f from x equals a to x equals b is given by this formula. I actually prefer this form. So I have 1/2, and then I have the sum. I use f of a and f of b once, and then I use all the other function values twice, and I'm multiplying by delta x, where delta x is b minus a divided by n. And I forgot to write it here, but it's an important part of the theorem. This sum approaches the value of the integral as n goes to infinity. So we'll say the approximation approaches that value as n goes to infinity. So if you take more trapezoids, use more trapezoids, you're going to get a better approximation. So we can do that for a particular function. Let's do that. Here's the example from the book. I'm just going to use the same one from the book. We have y equals sine of x, and we're interested in the interval from 0 to pi. Now, if we want to approximate this using trapezoids, we can use n equals 4 trapezoids. We can approximate that area under the curve, relatively easily by evaluating this function at 5 x values. The first x value is a, or 0. And the second one comes from taking that interval from 0 to pi and subdividing it into 4 equal pieces, or 4 intervals of equal width. So we're going to take b minus a and divide by n. So it's pi minus 0 and divided by 4. So we have pi over 4. So x naught is a, which is 0. Then x1 is a plus delta x. So we have 0 plus pi over 4. X2 is a plus delta x, so it would be 2 times delta x in general. So we'll have pi over 2. Then we'll have pi over 3 pi over 4, and then pi. So we're going to evaluate the function at 0, pi over 4, pi over 2, 3 pi over 4, and pi. So that's relatively easy to do. There are also special angles. So we can find those values relatively easily, probably remember them. Oops. We're evaluating at 0, pi over 4, pi over 2, 3 pi over 4, and pi. And I think we know these values. Sine of 0 is 0. And at pi over 4, we get square root of 2 divided by 2, which is about 0.707, I think. Then at pi over 2, we get 1. And at 3 pi over 2, we have that same square root of 2 over 2 again. That's about that approximately 0.707. And at pi, we get 0. Okay, so if I want to use the trapezoidal rule to estimate this area, I create a little trapezoid on each interval. I actually end up creating triangles on the last 2 intervals, don't I? But I've got trapezoids on those in the interior. The area is approximately this. Using the trapezoidal rule, we'll have 1/2 of y at 0 plus twice y at pi over 4 plus twice y at pi over 2 plus twice y at 3 pi over 4 plus y at pi. All of that times delta x, where delta x is that pi over 4. So we end up with 1/2 of 0 plus 2 times the square root of 2 over 2, which is square root of 2, plus 2 times 1, which is 2, plus 2 times the square root of 2 over 2 again, which gives us the square root of 2, plus 0 times delta x, which is pi over 4. So we end up with 2 plus 2 root 2 divided by 2 times pi over 4. And we can factor out a 2 in that numerator. And we can simplify those 2's. And so we get 1 plus the square root of 2 times pi, all divided by 4, excuse me. And we can use Desmos.com to get an approximation of that. So this is our picture. We've plotted all of those points, those 5 points, and we've drawn some line segments so that we can see the various areas that we're computing. Have the area of this trapezoid plus the area of this one plus the area of this one plus the area of this one. The exact value of the area under the curve from the on the interval from 0 to pi is 2, which we could have computed using the fundamental theorem and say, well, what's the antiderivative of sine of x? It's negative cosine of x, right? And then we could evaluate that at pi and 0 and subtract. Oops. And we get 2. So that's one way of evaluating the integral. Or we could use this trapezoidal method. And the trapezoidal method is something that I would use if this function was something that I couldn't take the antiderivative of. If I don't know what that closed form antiderivative is and I can't get an exact answer, I might use this. But it's still a good example to practice the computation. So you have 1/2 of the function value at the beginning, the function value at the end. We double all the function values in the middle, and then we multiply by that delta x. And we get this approximately 1.896. You might say, okay, well, what's the difference between that and the exact area under the curve? Well, it's just 2 minus that number. So our error is actually 0.103, but there's a theorem in the textbook. It says if f has a continuous second derivative on the interval from a to b, then the error in approximating the definite integral of f using the trapezoidal rule is less than the following maximum error. So here's our formula for the maximum error. It's going to be equal to b minus a, that's the length of our interval cubed, divided by 12 times n, that's the number of trapezoids squared, or the number of subintervals squared, times the maximum value of the absolute value of the second derivative of the original function on the interval of interest. So our function was sine of x. So when we compute f double prime, what we're going to get is negative sine of x. So the value or the maximum value of the negative sine of x, we know when we compute the absolute value of that, the maximum is 1. So the error, the maximum error comes from taking b minus a and cubing it. So it's pi minus 3 cubed divided by 12 times that 4 subintervals squared, or 4 trapezoids squared, times the maximum value of the second derivative on the interval, which is just 1. And so we say, this is our upper limit on the error. That means we're going to be, we can be sure that the trapezoidal rule is going to give us an answer within 0.16149 of the exact answer. Now, it turns out that the actual error is less than this maximum error. The actual error for this particular function was 0.10388 approximately. Now, we can do the same thing that we just did. We did it on paper here on the computer with a different graph. I'm using 8 trapezoids rather than using 4 trapezoids. So let's do that. So here's our picture. We've got those 9 points on the graph, one at the end of, at the beginning and then the end of each subinterval. In this case, our delta x is b minus a, so that's pi minus 0 divided by 8. So we're using 8 trapezoids. And we do pretty much the same thing when we use the trapezoidal rule. We evaluate f at 0 and pi, we evaluate them once. We double all of the function values in between. Because again, we're counting that edge in the middle. We're counting it twice. We're counting it for the first trapezoid and then the second trapezoid, or the I minus 1th trapezoid and the ith trapezoid. So we add all of those together. We multiply by 1/2 because that's part of the formula for the area of a trapezoid. And we multiply by delta x and we get a 1.97 that's a better approximation than we had last time. So if we look at the difference between the actual value and the approximation using the trapezoidal rule, our actual error is 0.02576 approximately. So it's very, very small, 0.025. Our maximum error can be computed using the same formula. The second derivative is still negative sine of x. So we get negative, or pi minus 0, that's our interval length cubed, divided by 12 times the number of subintervals squared. So when we use the trapezoidal rule in general, for this particular function, we would expect the error to be less than 0.04. And it turns out that it's even less than that. The actual error is actually equal to 0.0257. So that's the trapezoidal rule. Hopefully you feel comfortable with it. You understand where it comes from, because we're just taking the area of this first trapezoid, the area of the next one, and the next one, and the next one, and the next one. And then we say, okay, whenever we do that, as we go from sort of segment to segment, we're counting these y values in the middle twice, which is why we've got 2 multiplying those y values in the middle for our function. But we only use the y values at the end once for that first trapezoid and the last trapezoid. And the formula for the area of a trapezoid is 1/2 of the quantity base 1 plus base 2 times height. The delta x is always our height because we're sort of looking at those trapezoids sideways. And the bases are the function value on one side and then the function value on the other. So that's how we get that. We've got all those little trapezoids there. And this is the code too. I couldn't find a way to do this more efficiently, so I just ended up typing a lot of points and typing a lot of intervals and having the Desmos shade them. There's got to be a much more efficient way. But for some reason I was having trouble getting Desmos to work that way today. Those are pretty picture. And theoretically, if we take the limit as the number of trapezoids goes to infinity, we can get that error even smaller than that 0.025 that it already is. That's that. In the next video, we'll look at our next numerical integration technique, which is called Simpson's rule.